that the Earth was enshrouded by a belt of charged particles. A couple of years later, Mariner discovered that there was a solar wind, a wind that was blowing off the star. And at that point, we had discovered and codified two important things. One of them is that particles and fields are ejected by the sun. And these are two of the ways that the sun, or a star, communicates with the universe. Now, we've been looking at pictures of an active sun taken a few years ago. And we will occasionally see little sparky things that look like snow. And those are charged high-energy particles going through the detectors. Now, the research and the events have led to the development of a study, a formal study, of the interaction of gravity, pressure, and magnetic fields. And this is called heliophysics, a relatively new science. The research benefits from this have proven to be not only of value culturally and intellectually, but they have some research benefit and value to our society in the sense that they are politically important and they have economic impact. And these impacts are on our modern society, both civil and military. Now, as a consequence of our last decade of research in space, we are today poised at the beginning of a new magnetic activity cycle. And let me have the last slide, if I could, please. And we were able to study the sun and its activities inside and outside, its ejections as they go forward out of the sun's atmosphere. And then you can see the Earth enshrouded in this protective blue magnetic field over on the right-hand side. Our spacecraft are used to study this system. It's a systemic investigation. And the SDO is the cornerstone foundation mission for the next decade of solar research. Now, to tell you more about SDO and its program, I'm going to turn this over to Lika, and she's going to talk about the Living with a Star program and SDO.
Thank you, Dick. We live in the extended outer atmosphere of the sun. And in that sense, we truly live with this star. Even though to the naked eyes, the sun appears to be a constant pale yellow ball, the sun, it's only a limitation of human eyes. The sun is really not a constant. In fact, modern telescopes and spacecraft have really penetrated the blinding glare of the sun and have found sort of a maelstrom of unpredictable turmoil. As Dick mentioned, and I want to repeat this, the sun is a variable star. It is a magnetic variable star, and this magnetic variability drives every cubic inch of space in this solar system. While sunlight enables and sustains life, the sun's variability produces streams of high-energy particles and radiation that can harm life and even alter its evolution. If I can have the first movie, please. What you're going to see here is a cloud of plasma that's breaking away from the solar surface. These are called coronal mass ejections. It's really charged particles that will travel at tremendous speed, sometimes millions of miles an hour, and go through the interplanetary medium, impinge on Earth's magnetosphere. The blue lines that you see are imaginary field lines, which gives you the shape of the cocoon of Earth, which is the magnetosphere. Most of the time, these particles do not penetrate Earth's environment. They are deflected by this shield, the cocoon. But every once in a while, when the field of sun and Earth are just aligned right, these particles will actually propagate through the poles of the north and south poles of the Earth. And what you see are these particles going in, and they will create beautiful aurorae, both in the north and in the south. That's the beautiful aspect of these particles. But it can also produce harmful effect in our space environment, and I'll talk about that just shortly. So what you can see from this movie is that the origins and fate of life on Earth are intimately connected to the way the Earth responds to the sun's variations. Recognizing this importance, in 2001, NASA initiated a program called Living with a Star, whose goal is to study the sun as a variable star and its impact on life and society. If I can get the next impact slide, please, and talk about why, what is the rationale behind studying this sun. After all, it's an ordinary star. If you look at the upper half of this slide, what you will see is this variability that we talked about, what it does to Earth's magnetosphere, ionosphere, mesosphere. Wherever there is magnetic field, the sun really dominates that environment. We also, this variability affects every planetary environment in the solar system. And of course, we are really looking at the basic plasma physical processes. And these are universal processes of heliophysics that Dick talked about. And that's what we are trying to understand. It's true for everything we do, I think, in the universe. The lower half of this actually shows the impact of this variability on Earth, what happens there. We have increased dependence on space-based systems. I mean, that's very clear. Our modern way of life is just intimately connected to technology that is driven by this solar variability. Solar variability, as you can see, can affect human in space, satellite operations, smart power grids, GPS navigation, emergency radio communications, air travel, financial services, you name it, and I'm sure we can find a chain that connects it to the sun, and also terrestrial climate. Thus, understanding solar variability is crucial to our modern way of life, which depends on it. So I want to say two things about the mission Solar Dynamics Observatory. SDO is the solar variability mission. It is going to revolutionize our view of the sun, and it will reveal how solar activity affects our planet and help us anticipate what lies ahead. SDO is designed to probe solar variability unlike any other mission at NASA or even internationally. It will observe the sun faster, deeper, and in greater detail than any previous observations, breaking barriers of time, scale, and clarity that have long blocked progress in solar physics. And I'm going to pass it on to Dwayne now.
Okay. Thank you, Richard and Lika. Now we'll switch down to the Kennedy Space Center, where Dean and Liz, go ahead.
Right. Thanks, Dwayne. I'm Dean Pesnell, the project scientist of SDO. Together with our science team partners at the University of Colorado, Stanford University, and the Lockheed Martin Solar and Astrophysical Laboratory, we will run SDO, analyze the data, and produce the science of SDO. So I'm here today to talk about some of the science we will do with the instruments. First, let's look at an image of the spacecraft. Here we see the helioseismic and magnetic imager, HMI, the atmospheric imaging assembly, AIA, and the extreme ultraviolet variability experiment. As our sun affects our life more and more, as we come to depend more and more on technology, most of these effects come from the ever-changing magnetic field of the sun. SDO is designed to study that magnetic field from its creation to its destruction and how it then can affect the Earth. Predicting this magnetic field is one of the goals of SDO and Living with a Star. We use helioseismology to study the movement of material inside the sun that creates the magnetic field in the solar dynamo. Here we have a picture of small changes in the rotation of the sun that were produced by a study of the sound waves rippling across the sun. One bright band moves towards the equator in both hemispheres. In the past solar cycle, we noticed that active regions or sunspots appeared only in and above that band. We will use HMI to make measurements in the upcoming solar cycle to see if that allows us to predict the timing and magnitude of upcoming solar cycles. We will also use HMI to study the surface magnetic field of the sun. Here is an image of the historical information we have. Unlike this image, which only shows the strength of the magnetic field, HMI will also measure the direction of that field. Scientists feel that knowing the direction of the field will help us to make better predictions of when flares and coronal mass ejections will occur. Once the field is out of the surface, we see the field illuminated by hot gas that is forced to flow along the field lines. Here we have two images from the SOHO spacecraft. On the left, we see an image that shows material at a temperature of 1.5 million Kelvin. On the right, we see three different temperatures